Hello, relativity friends. Uh, I've been goofing off here with Minkowski space-time and the equations of that, and it's a lot of fun. I wanted to share it with you. So, what we're talking about here is a example. You would be in a rocket ship or something, way out in space, far, far away from any large gravitational fields. And so they would call that flat space. So it has no curvature because there's no gravitational fields are present. And so this is the thought experiment that Hermann Minkowski went through a few years after Einstein published the paper on relativity. And he came up with a geometrical way of looking at this space, and it's now called the Minkowski spacetime. And what it actually is a hyperbolic geometry. All right. This looks like the plain old Euclidean space you're used to doing all your work in, but it's not. It's not Euclidean. It is non Euclidean. It is hyperbolic. Okay. So what we have here is we have some x. So this is obviously 2 dimensions because I can't draw 4 dimensions. I don't know anyone that can. So we have some spatial component x, we have some time component, the ct, okay? Now, the convention is that you arrange the coordinates such that the speed of light bisects this at 45 degrees, all right? So we go over some 10 units over and 10 units up. So this could be like 10 light seconds, and this could be 10 seconds. All right. So the time it takes light to travel the 10 seconds. So that's why they do it this way, because nobody wants to write those enormous numbers or very small numbers on a graph. It's very hard to work with. All right. So now we have this going in this light going in this direction and this direction, but we also got one going in the other direction, right? So this beam of light could be traveling in this direction or that direction. These parts here are called the light cones. So as an example, this is the past and this is the future. And you can't go that direction, unfortunately. You can only go this direction. All right? So what's fun here is that if you plot the equation for the space-time interval, which looks like this, so the change in, let's say, 2 events squared is equal to the speed of light squared times the change in the time the coordinate squared minus the change in the space coordinate squared. If you plot this, it looks like this. They're hyperbolas, right? So even though I said this is rectangular and it looks Euclidean, it's not. It's a hyperbolic space, okay? So let's get rid of that because we don't need it. Let's get rid of that because we don't need it, because we're just going to work in this quadrant here, all right? So let's put down a point in here, which they call an event, all right? So when something happens in space-time, it's called an event. And it has the coordinates. It has 8, the space, the coordinates, and 12 time the coordinates, all right? And we can put a line segment from that to the origin and say, hey, what is the magnitude of this? So maybe that's a vector or something, right? Or a line segment or displacement vector. They're all the same thing. So in Euclidean space, you would go, oh, well, it's this triangle right here. So it's this squared plus that squared is equal to this squared. That's wrong. You can't do that because it isn't Euclidean space. So the saying goes, you can't trust your eyes in space time. You have to use the metric. You have to use this. Nothing else will work. So somewhere here I got the equation, okay? So you square your time the coordinate, subtract the space the coordinate, take the square root of it, and this is the magnitude. Now, if you had done this in Euclidean space, that would be a plus sign, and you would have gotten the wrong answer. All right. So that's kind of fun. So let's take that off. And now we're going to get to the meat of it. This square frame you see here is a person at rest. This is a person at rest. And since they're not moving in space, but they're still moving in time. So time is passing, but I'm not going anywhere. I'm just sitting here, but time is passing. So I'm moving up this scale like this. And they call that my world line. That's the terminology they use, my world line. And uh, it's typically drawn on the time axis. Okay. Now let's draw the world line of someone traveling with a constant velocity in the positive x direction. So they're moving in the positive x direction at a constant velocity. And here they are. So this is their world line. So every 10 units of space, they're traveling 20 units of time. So that means that they have a slope of one half of this, which means they're traveling at 50% the speed of light. So that's what this means. All right. So what's interesting to know here is we calculated this magnitude of this line, this segment, on this frame of reference. Now, what is this event as an example? What is it in this frame of reference? Because this person and this person will not agree on this event. They won't agree on where it is, and they won't agree on what time it is. But they will agree on this invariant space-time interval. And that's what's fun about it. All right? So now that we've plotted this, which is its time axis, they call its world line, what about its spatial line? What about its spatial component? Where does that go? All right. Well, one of the postulates of special relativity is that the speed of light is a constant in all reference frames. So this is a constant. You can't change it. All right. So that means that this line, which is the speed of light, must not only bisect this frame, which is at rest, but it also must bisect this frame. So as this world line moves down, the spatial line has to move up by exactly the same amount. Let me blow this out so you can see. Do you see how this bisects? So this angle is equal to that angle, and this angle is equal to that angle. So that's what that means. All right. So since we know that the speed of light is a constant in both frames as reference, that's why we can actually use the space-time interval, because in the rest frame of reference, I get this answer, and in the moving frame of reference, I get this answer if I use that interval. Okay. So now, when we were trying to determine this magnitude, we used these the grid lines, right? Because we were in the frame of reference at rest. And to do that, as an example, we drop this vertical following this axis down to here. We drop this horizontal following this axis down to here to get our numbers. Well, we have to do the same thing now in this frame of reference. So we have to drop a line that is parallel to this time axis here, and we have to drop a line down to here that is. Let me show you rather than trying to stumble my way through this. Okay, where are those numbers? They are right here. No, they are. You would think I'd have this better organized, wouldn't you? But I didn't. Okay, so here is this point projected onto this axis. Let me get rid of the speed of light. Gone. All right. So what I'm doing is projecting this point onto this spatial axis, but I have to follow this parallel to this time axis. All right. And now I do the same thing on the other side, which is here. And I project this point onto here, onto the time axis, staying parallel to the space axis. All right. So now you're like, well, okay, but what do we do now? Well, we have to find out what that number is and this number is. Well, you can't just count over like this, one, two, two and a half, up something. You can't do that. You have to count here. Well, you say, well, I can't count there because I don't know what these numbers are. That's right. You don't know what these numbers are. This metric is different than this metric because this coordinate, the system inside here, inside this V, it's all skewed and stretched, and you don't know which way it goes. You don't know how long the basis vectors are. You don't know what the angle is. You can calculate all that if you want to hurt yourself, but I'm not going to. All right. So we need to count this, and then we need to count this too. Here, we need to count up to this. What's that? We don't know. Well, that's why God invented the Lorent transforms. So these transforms take a coordinate system in one frame of reference and give you the coordinates in another frame of reference by using these relativistic, the parts of the equation. So this says that, and the zeros now are the rest frame and the ones are the moving frame. And you see they've got this thing beta and gamma in here. Well, beta is ever how fast you're going. So it's your velocity over the speed of light, which was 50% or 0.5. And gamma is 1 over the square root of 1 minus the beta squared. And so you plug this in here and you get 1.15. So now we can just put these two numbers in these two equations and solve for what are those points. So let's go do that. All right. So here's our beta. We wrote that down. Here's our gamma, the function. It turns out to be 1.15. Now let's do our first calculation, which is this one here. All right. So we got T1 equals gamma times T naught minus beta x naught. And we know what x naught is 8 and CT naught is 12. All right, so we get this number. So this is 9.237 on the time axis. Well, you go look at this and you're like, well, I don't know what that is. I mean, you'd have to count up here like this. I don't know. Well, that's why you use these equations. So it's 9.2. Now let's find the space number. The space number, the number on the space axis. All right. So it's given by this equation, and it's 2.3. Well, you say, well, that's 2.3. Well, it could be. Who knows? Well, I don't care. The reason is because now I'm going to plug it into the invariant space-time interval equation, and I get 8.9. Well, what did I get up here for the other one? 8.9. So bada bing, it works. When you want to know the difference between two events, in our case, one of the events was 0, so we didn't have to worry about it. And this event here, you use the space-time interval, and you get the answer. Anyway, I thought that's fun. I'll see you later.